This presentation is a continuation of the Introduction to Hypothesis Testing. P-values. Assuming the null hypothesis is true, the p-value represents the probability of getting results as extreme or more extreme than the sample that you're given. And if that p-value is very small, what that's telling you is it's telling you that your sample is very, very extreme compared to what was expected. And if that's the case, you might say that what we're expecting is wrong, therefore the null hypothesis is wrong. So in the event the p-value is small, we reject H0, and we write, there is sufficient evidence to conclude that the null hypothesis is unlikely true, therefore the evidence supports the alternate hypothesis. If the p-value is large, that means that what you have is not that extreme, that you can indeed get samples as extreme or more extreme, assuming the null hypothesis is true. So if the p-value is large, we fail to reject H0. We never say accept H0, and instead we write, there is insufficient evidence to conclude that the alternate hypothesis is true. The null hypothesis may be true, but of course we cannot be sure. We never say H0 is true, we never say accept H0, we never say there is evidence supporting H0. It's either reject H0 or fail to reject H0. Here's a two-tailed example. Mu equals 100 versus mu does not equal 100. And here is our sample. So how extreme is this sample? 105? Well, that's 5 more than the average. This is a two-tailed example because it's not equal. So we've got to think about ones that are too small as well. Well, using symmetry, 5 less than the mean would be 95. So we want to find numbers that are as extreme as the one we're given, which will be more than 105 or less than 95, and identify those probabilities. So here we want to assume the null hypothesis is true. And we want to find the probability that a random sample of 43 would have a mean as extreme or more extreme, that is more than 105 or less than 95. That probability is the p-value, and depending on the results of the p-value, we will either reject H0 if the p-value is small, or fail to reject H0 if the p-value is large. So here's a Minitab simulation we're going to do. We're going to take 10,000 numbers, put them into C1 to C43. Those numbers are going to come from a normal distribution with a mean of 100. Why? Because we assumed in H0 that mu equals 100 and a sigma of 20. Why? We don't know what sigma is, but we have an S of 20, so that's going to be our best approximation. Now we're going to take a mean of those 43 numbers and put them into C45, and then sort those numbers into C46. So C46 will be a column of sorted means. So what shall we ask Minitab? How many of our means are more extreme than 105? So what exactly does that mean? How many are more than 105 or less than 95? And we'll check Minitab for those results. So here's our syntax. Random 10,000 C1 to C43, normal 120. Our mean C1 to C43 put into C45, sort C45, C46. And we want to examine C46, and our first question is going to be, how many of these numbers are less than 95? So we see 492 for sure are less than 95, but this 95.000 is an interesting one. So let's click on that. That is 94.999779, so that is also less than 95. So we have a total of 493 out of 10,000 that are less than 95. So our approximate probability that x bar is less than 95 is about 0.0493. But this is a two-tailed test, so I also have to find how many are greater than 105. Okay, scrolling through our list, we see 9,533 are less than 105. So that would mean the balance are greater than 105. So the probability x bar is greater than 105 should be about 467. That's how many more there are to get to 10,000. So there's the numbers on the left tail, there's the ones on the right, and if we put those together, that'll give us an approximate p-value. Our approximate p-value is 0.096, which is, of course, relatively high. And when the p-value is relatively high, we fail to reject H0. How do we define high and not high? Well, a p-value is high if it's more than 0.05, it's low if it's less than 0.05. In some circumstances, you might consider 0.01. But here, for the most part, we're going to use 0.05 to define a large or a small p-value. So here's our example. We said based on our Minitab simulation, we expect the p-value somewhere near 0.096. That is large. The conclusion is fail to reject H0. And we write there is not enough evidence to conclude that the sample comes from a population with a mean different from 100. The population mean may be 100. We cannot be sure. Assuming the population mean is 100, the chances of getting numbers this extreme or more extreme is almost 10%, and 10% is fairly large. Since that's fairly large, we say this might be true. So here are the standards we want for hypothesis testing. Always state H0 and HA. In later presentations, we'll talk about how we compute the test statistic. In these examples, you've looked at how we identify the p-value, and we're going to look at some other ways to do that as well. Once we have the p-value, we either reject H0 or fail to reject H0. And maybe most importantly, once all that's finished, you need to state a conclusion in context. So to examine these 5 properties, we are going to look at a real-world problem. So a pollster believes his candidate has the support of more than 50% of the registered voters. He randomly selects 500 voters and finds that 265 support his candidate. Is he correct? Can he conclude that of all registered voters, of the entire population, can he conclude that more than half will support his candidate? So here's our H0 and our HA. The population proportion P equals 0.5 versus the population proportion P is greater than 0.5. And we're going to go to Minitab to solve this problem, and later on I will actually show you how to compute the test statistic. So stat basic statistics 1 proportion. You will notice I have 2 buttons, either samples and columns or summarized data. I want it in the summarized data, and the number of events, 265 people support his candidate out of 500. This button is to perform a hypothesis test, and of course we want to perform a hypothesis test. The 0.5 comes from the fact that P equals 0.5 is our H0. So whatever you're comparing a proportion to has to go in that box. Then we're going to go to options. Confidence level is 95. Well, that's for the interval, which isn't quite relevant here. But I do have 3 choices for the alternate hypothesis. Could be less than, could be not equal, could be greater than, and I'm choosing greater than. Then you'll also notice we have this button. This button is to use the test and interval based on the normal distribution, which is what we typically do, appealing to the normal approximation to the binomial. So we're going to say OK here. We're going to say OK here. And you'll notice what it gives us. Test of P equals 0.5. So this is H0 versus P is greater than 0.5. That's HA. We have information here, X and sample P, P hat is 0.53. Our Z value is 1.34, and our P value is 0.09. And that P value, again, very similar to the one we had before, is a high P value, a large P value, and in that case we will fail to reject H0. So let's look at our 5 requirements again. First off, H0 and HA, which we have stated here. Next, I want to state the test statistic. Test statistic Z is 1.34, which we have here. Third, we're going to state the p-value. P-value is 0.090, which is a high p-value. So based on that, we're going to say since the p-value is large, we fail to reject H0. And then we have to ask ourselves, what does this tell us in context? The researcher wanted to conclude that more than half of all registered voters supported his candidate, but we failed to reject H0. So H0 was P equals 0.5. It could be 0.5. He does not have enough information to conclude that more than 50% of the entire population of registered voters will support his candidate. And that concludes this presentation.